All right, here we are with graph number 3, 4. Yeah, cotangent, the last guy. All right, so I want you to remember tangent didn't exist at pi over 2 and negative pi over 2. It did have a value at 0, 0. That's because it's sine over cosine. So 0 over 1 works for tangent. The cotangent is the reciprocal. So everywhere tangent was 0, cotangent has an asymptote. Everywhere that tangent had an asymptote, cosine has a 0. Now, because of the weird behavior, cotangent ends up being this weird flip. Because between 0 and pi over 2, all of our trig functions are positive. So I have an asymptote at 0, pi over 2 is going to be equal to 0, and I want those numbers to be positive. So that forces the next part to be negative, and then it repeats with that pi period of pi. So this is not the correct formula for the period. This is not the correct formula for the domain. This is not the correct formula for the asymptotes. There should be division symbols in there. The same as we had in the previous section. Our asymptotes occur at pi over b k. Now we can also horizontally and vertically shift this guy around, but our focus is going to be on where's the asymptote go, and then where does that pi over 2 point go, and then the halfway between will go up to 1. Just like on tangent, the halfway between 1 up to 1, it's just on this one, they'll be backwards. All right. All right, so our A value is 4. Our period is going to be pi divided by pi over 8. So our period is 8 units wide. And then a horizontal shift, the inside of that would be pi over 8 times x minus, if I multiplied by 4, I would get back to pi over 2. So this is going to be 4 units right. And we also have 2 units down. All right, let's see what we can make of this. All right, so 4 units right. Sorry about that. Just tried to put one more tick mark and it was right on the scrolly line. All right, so that is 12 because our period is 8 units wide. So it's going to go from 4 to 12 for a period. All right. And it's going to go 2 units down. And then from that, we have to count our amplitude. So it'll be another 4 units down. Then from our 2 down, 1, 2, 3, 4, up. All right, so 4 units right and 2 units down. There is where the new center of the graph is. Now, for me to remember which graph is which, I either would punch it in my graphing calculator, because when I was in school, they let me have one, or I would have to go back to the definition. So cotangent is cosine over sine. So wherever sine is 0, that is where the asymptotes of cotangent are. So sine is normally 0 at 0. So that means this 0, 0 point I got is actually an asymptote. So let's sketch that in. And that means over here then, 1 period width away will be the next asymptote. All right, so asymptotes occur at 4 plus 8k. So 8 for the width, 4 for our starting value, where k is any inch. Now our halfway mark, halfway between 4 and 12 is 8. And then remember, in the first region of the graph between the asymptote and the 0 point, the graph is going to be coming from infinity to go to 0. So we know it's going to go that way. But the figuring out where part, that's where our, oops, I forgot what that value also got shifted down to. Now from our 0 line, from our midpoint, we're going to go halfway between, and then from our midline, 1, 2, 3, 4, we get our point there, and then from our new 0, 1, 2 over, and then the 4 down, way at -6, and then just kind of curve it a little. But there it is, including our formulas for where the asymptotes would occur. Because that's what it really asks on the web work, a whole bunch of, what's the formula for the asymptotes? And for me to figure that out, I may as well just sketch the graph. Now, one last, it was a word problem, which, like, I know, math land, word problems don't necessarily make sense, but there is still a little bit of value in at least being exposed to it and thinking through it, thinking what these things would represent in a real context, quasi-real. So we have a function, y equals 5 tangent of pi over 4t. This is going to mark the distance in the movement of a light beam from the top of a police car across a wall, where t is our time in seconds, and y is the distance in feet from a point on the wall directly across from the police car. All right, so I'm going to go with a kind of vertical picture here. All right, so here's our police light. And you know how they spin around and around. And then we have a wall. So our distance in feet from the siren to the wall, like this is the shortest one. Like, so this is the point on the wall. That's the point on the wall directly across from the police car. So the point is going to move to the right, and then eventually it's going to like off the wall, but then the other side is going to come in and be coming from the left side and on the wall. So that when it's off the wall and the beam of light is parallel to the wall, that's where our asymptotes are going to be, because the light is not on the wall at that theoretical point. All right, so they said find and interpret the stretching factor and the period. Okay, so our stretching factor, let's start with our period first. All right, so the period is pi, because it's a tangent graph, over pi over 4. So our period is 4. So what that means is every 4 seconds, the starting point would be the starting point of the next repetition. So that means it takes 4 seconds for the beam of light to travel completely across the wall, or for the police siren to make half a rotation. But I say this is seconds because t is our input, and period is a width we're seeing on the graph, so that's an x distance. So 4 seconds. And let me go ahead and type that. So every 4 seconds, the point of light is start, meaning every 4 seconds, the, all right. So there's a little bit of a flaw here. We don't know if this is a single-sided or a double-sided siren. So like the light, you have a light and then a mirror around it, and that's what causes the like circular light that you see traveling. So older sirens, it's just the one thing and it rotates around. Newer sirens, though, it's like 2 of the cups. So when it goes 180 degrees, the next beam of light is there. So every 4 seconds, we get a new beam of light. So we don't know if that means 180 or 360 for the siren. It doesn't actually matter for us. It just, that's how long it takes for a cycle to occur. All right. So our y value is the distance in feet from a point on the wall across from the police officer. So it's measuring how far away from that center mark it is. So it's like telling us, where does this point go? So our 0 for y is going to be, it's at that point directly across. And then as the time goes, the y gets big, 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 shoot off, come back, small, small, small. All right, and then our 5 number. So the 5, remember, impacts the like corner points on the tangent graph from being over a quarter of the period up 1. Now it's going to go up 5. So I know what that means on the graph. I'm still kind of thinking about what does that mean in the context of the problem. So let's go ahead and do B. We're going to graph on, don't know why they want the interval 0, 5, but sure. All right, so tangent is sine over cosine. Sine starts at 0, so tangent starts at 0. All right, and then our period is 4 seconds, but they want us to graph all the way to 5 for some reason. So let's 2, 3, 4, 5. Now remember, this point on the graph is the center of a period. So that means we're actually going to see asymptotes at 2 and 4. Nope, not at 4. So at 2 and -2. So then the next one after that would actually be at 6. Now from our 0 point, so this is 2 seconds. So this is 1 second. And on 3, 4, 5. So our y value is going to be from -5 to 5. So now my secondary points are there and there, but it's going to take a while just based on how we drew it to get over to those asymptotes. And then again, same thing. So this will be down at the tick mark. This will be up at the tick mark and up, down. All right, so after 1 second, our y value is 5 feet. So after 1 second, we're 5 feet along the wall. Past that, up to 2 seconds, it's going to travel a lot faster along the wall. And in calculus, like we could actually use this function to figure out that speed, but it's going to move kind of slow between our -5 feet and our 5 feet. Like the graph has a lot more values here. Like not more, but it's just whenever a graph is coming to 0, like that's where things tend to slow down. So we can see this movement from the -1 seconds to 1 second. It's a lot easier to like visually track the thing moving. But from the like 1 to 2 seconds, that's where it's like gone off the wall. It's about to go parallel to the wall. And then the next second after that, yeah, it depends on it's coming back around. All right, so well, we kind of did see here, evaluate f of 1. F of 1 is 5. So that means at 1 second, let's say the light beam is 5 feet away from the point across from the police car on the wall. English sense is kicking in, so from the point on the wall across from the police car. So I guess it's just the stretching factor is giving us like kind of how far the beam of light is moving on the wall relative to that center point. Yeah. I mean, if our stretch factor was smaller, then the beam would not be rotating as fast because then it would be after a second, it'd only be 2 feet along. So the siren itself, like, is still spinning at the constant rate, But this 5 feet along the wall is also like, presumably we could do some math to figure out how far from the wall the police siren is. Yeah. So even I'm kind of like, I still don't like this application problem. No, this is not something you would do in a real course. I apologize for not having that knowledge yet. That is the end of this section. So it's mainly just focus on where are the asymptotes.